Thank you for coming to this meetup, and thanks for staying for our talk on Bullet. So Nate and I will be giving this talk. Nate will be giving you information about architecture, performance numbers, and kind of what we're looking to do for the future. And I will be doing the other stuff. So let's jump into it. So how do we get to Bullet? So we had a problem we had to solve called instrumentation validation. So instrumentation is a little bit of code that you have either on your website or in your app. It's generally responsible for logging some sort of useful information for you to be able to analyze later. And this is generally critical in most all systems for decision making. So you want to be able to really check that, make sure it's accurate, correct, if you have core things that are driven by that. Unfortunately, most systems, when you try to do data validation by releasing an app, doing something in it, and then waiting for the data to come back, you're going to be waiting for a really long time. Most systems are batch processing systems, and you're going to probably wait hours for data to become available. There might be good interfaces like Hive or Pig to consume that data if this is like a Hadoop ecosystem, but it's going to be slow. There are faster options if you have a stream processing system available to you, but that's going to be difficult to work with. But if we could somehow kind of squeeze those two things together, some sort of stream processing system with easy queryability and light queries, that might be what we would be looking for. Unfortunately, that's not what typical query engines look like. So let's just go through what a normal query engine looked like. I'm sure you guys are very familiar with this. All these things start with data, right? You need data to do something. When you have data, then you put it somewhere. And once you have data somewhere, you can start doing things with it. You can run different queries. The problem is queries tend to run at different times. They tend to look in different things and maybe even look at the same things. They tend to be very inefficient in terms of sharing resources. Another approach is what we'll call a look-forward query engine. So we once again start with data, but we're going to no longer put it anywhere. We're just going to operate directly on that stream, right? So we're going to throw a little net over our stream of data. And now we're going to start operating on the data as it's flowing in. Now, there's probably three categories of data in this. One is what I'll call future queryable data. This is data that's going to arrive soon. We will then be able to do something with it. There's data that has arrived, which we can inspect and evaluate. And there's data that has passed us. Once it's passed, it's done. We can't do a replay. We can't look at it anymore. And the great thing here is you can start running multiple queries at once as the data is flowing through. This is a little abstract. Here's what this looks in practice for both these systems. So this is for us internally at Yahoo. So one data source we have that's common is Kafka. And you can run different queries or jobs against Kafka datasets, right? For us, we are heavy Storm users. So maybe you're running 3 Storm queries. And we also use Spark as well. Now, what does the cost look like for this? If we have, say, 2 million events per second, and it takes, say, 1,000 events per second per core in terms of throughput, it's going to take you 2,000 cores per query to just consume the data. And if you have 4 queries, that's going to take 8,000 cores. And for hardware that we have, that's something around maybe 48 cores per machine. We're talking about 200 machines to just execute these 4 queries. Now with Bullet, these things look slightly different. We once again start with data. But now we're going to have Bullet handle the reading as a layer on top of Storm or potentially Spark. And instead of running your own Apache Spark or Storm jobs, you will instead submit queries into Bullet. So we can once again run our 4 queries. Let's see what the cost looks like now. So say 2 million events, same throughput, but the resource utilization to read is 2,000 cores. But now the read is being shared between the queries. And from our perspective, actually, the queries end up being negligible in terms of execution. The read tends to be the expensive part. And so they're negligible, and we're just that read cost is what we have to pay. All right, so what is Bullet? It retrieves data that arrives after query submission, right? Normal system, data arrives, we query. In this system, we submit the query and then look at data as it's coming through the system, look forward. We have no persistence layer. And this allows us to be really lightweight, fast, and scalable since we don't eat storage and the costs of reading are kind of fixed for us once we scale up. We provide a UI for ad hoc queries. We provide an API for programmatic queries. And the great thing about the system is it's pluggable, right? I said Kafka, but you can read from any data source that you would want, as well as you can run the system on different stream processing engines as it's a application layer on top. Right now, like I said, we have the Storm and Spark layers because those are the ones that are popular internally. All right, so just to summarize, what it's for: single stream, multiple consumers, ad hoc interactive usage, programmatic short-lived queries. What it's not for: repeatable queries. Now, you can run the same query multiple times, but what you can't do is probably get the same exact results, right? Because you're looking at a different set of data each time, the results can potentially be different. We don't supply any kind of joins currently, but it's something we do want to look into moving forward. And this is not meant for your heavy-duty ETL jobs, right? This is meant as lightweight queries that you can inject into the system. Now that I've talked enough about it, let me quickly show you what this looks like. So I have a few pre-built queries. All right, so here's a pre-built query that kind of shows you the speed of the system. So we have something called My Events. So this will give you all the events that I generate on the Yahoo network. So in this case, what we've put into the filter section is a bcookie filter. So this has my bcookie, and so this will give me events only that are mine. Now, how will you know that these are actually my events? So we've projected a set of fields that will hopefully help identify this as me: search term, age, gender, city for where we're located, ISP, I'll explain this in a second, and site, which is kind of what we visited. And this will write out all the records that I generate in a 30-second window. Now, we promised this was going to be really fast, but what you see is there's no data actually showing up. And there's no data showing up because I'm not actually doing right now anything on the Yahoo network. But I have this window open here, and let's type in yahoo.com. And boom, it says that we are visiting there. I'm going to do a search. Let's search for Hanukkah. And then you'll see Hanukkah's popping up here. And we'll just keep going down. Let's also try Hanukkah blessings, Hanukkah blessings transliteration, and we're out of suggestions. And the query's over anyways. And so now we can look at the results we saw of my interacting with the web page to kind of prove that it was me. So I am 35 years old. We are in Sunnyvale. I am male. And the ISP here, you'll see is Yahoo Inc. And that's basically when you're on the internal network here, that's what the ISP shows up at, a little proof that it was me. And then you can see that we visited two sites: front page, which is what we call yahoo.com, and then search yahoo.com. You can see on front page, obviously there's no search terms because I typed that directly into the URL. And once we went to search, then you can start seeing my search terms, which were Hanukkah. Let's expand this so it's easier. Hanukkah blessings, and that one thing I don't know what it is, Hanukkah blessings transliteration. Okay, so that's a basic query of how to find your data. And this is what people use when they would be doing the sort of instrumentation validation. They would generate data, find it, and validate to make sure it looks like what they want. All right, back to some details. So when querying Bullet, what can you do? So I kind of showed two things from these bullet points. One is the support for filtering logical operators on type data. You saw that with my filters, and there were data types involved there. You saw that queries have lifespans in this case, right? We set that query to run for 30 seconds as a way of terminating it. Two things we didn't go into was the fact that you can also do aggregations with the system. You can do things like group by, count distinct, top K distributions, and these are all data sketch-based aggregations. And I'll get to a little bit to why they're data sketch-based and what the benefits of that are. In addition, there is windowing. Now, there was actually windowing in action, which is how each individual event was being streamed back, but not be as obvious. So I'm going to get into a little bit more of this aggregations and windowing. And these are things that we went through to implement after we did the sort of live event capture, because we got additional use cases from people saying, well, I want to see when I do even validation, things like count distinct values in a time period, or I want to be able to look at distributions of things, maybe like gender distributions within my data set, things like that. I want to run very quickly and lightweight without having to run an expensive query. And so we started down this road. And aggregations tend to be fairly expensive to implement in a streaming system without leading to skew and other problems. So to demonstrate this, let me try a simple example that we're all familiar with, which is doing a count distinct. So a naive count distinct would look like this in a streaming system. You would read the input, you'd round robin it to like some bolts. This is like a storm way of doing it. Then you would extract your field that you're trying to do a count distinct on, and you send it to a single combiner who's responsible for counting the distincts. And this has obviously two problems. One is if you have way too many distinct values and it's trying to buffer all of this in memory, it's going to run out of memory. The other issue potentially could be maybe it's still a low number of cardinality, but the volume of data that's being sent to this one could overwhelm that one combiner, causing some other crashes or data to be dropped on the floor somewhere. So this is not going to work. So a more typical approach that you'll see is, again, read data, round robin, extract your field. But now what we're going to do is we're going to hash partition, right? So we make sure that a set of distinct values flows to one and only one processor in this case. Each one of those processors can then do its own count distinct, pass along its count, and then you get the total. In this way, you're no longer need to send more than a few values to the combiner. So that means the both volume and cardinality thing no longer applies. But the volume thing is still a problem when you're doing your count distincts, right? If there's a skew in the data, you're still going to send a bunch of records potentially to just one of these processors, which can get overwhelmed in the same way that the combiner would have been overwhelmed in the initial example. Now with sketches, here's how things look. You read your input, you still round robin, but now you're going to build a sketch. So you're going to extract the field, you're going to put in a sketch, and you're going to do this for all the records that come in. And then once you're done with the data, you're going to send it to this one combiner who's going to merge all the sketches together and give you the answer. Now, this looks a lot like the naive solution, because it basically is. But why does it work in this case, but the naive solution doesn't work? The big difference is how sketches work. So sketches have a maximum in terms of memory footprint that they will take up. And you're basically doing what we did in the typical use case, where we're doing the distinct operation on each individual processor. And by having a fixed memory footprint, we know that we're not going to overwhelm this combiner because it will only get the level of parallelism times the size of those sketches. And sketches are mergeable, so you get the answer in that way. All right, I'll give you a little bit more information on these sketches, but basically it works. All right, so data sketches. So sketches are a class of stochastic streaming algorithms. They provide correct results up to a point. So if you have, say, a sketch of size 16,000, that means you can put 16,000 elements into the sketch and with 100% accuracy. But once you go to 16,001, the system is going to start doing an estimate for you. And you might say, oh, but then I don't know what the error rate is going to be when I merge across all these things. Well, you do. They actually have provable error bounds for all sizes of sketches. So if you want to be super accurate, you have a very large sketch. If you're willing to tolerate some level of error, but you want to lower your memory footprint, you can have a smaller sketch. And this fixed memory footprint is really great because it's predictable for you when you run jobs. Instead of worrying about overwhelming something, you know that no matter how much data skew there is, the sketch is not going to exceed the fixed size that we allocate to it up front. And what allows us to do is also they're mergeable, right? So this allows us to make non-additive operations additive, right? You can do a bunch of count distincts and then merge, basically do a bunch of distincts, then merge those together and then get the count. And it will dedupe it for you when you do the merge of the sketches. All right, now that we have how we do the aggregations with sketches, let's do a little bit about windowing. So what's the point of a window? It's to make a stream more digestible for you. It's the way to breaking it up instead of running a very long query with no feedback for you, right? The way to break up your stream is either by time, like say every 10 seconds do something, or maybe do something every 5 records. And for us, an increment or a digestible chunk is an individual window, and that's kind of what we return in our system. So there's a lot of windows. The ones with the red asterisks are the ones we actually have implemented. So a tumbling window is the most classic one you can think of, which is you return something every something. So like every 5 seconds, you would return all your records, or every 5 records, you would just return, but in a variable time window. Hopping windows are similar to tumbling windows, but they can overlap, right? So that would be, say, every 5 seconds, return me data for the last 10 seconds. And a sliding window you can think of as like a tail dash F, which will continuously give you the last set of records that you have in your system. So to better demonstrate this, we'll go in a little bit. So why is this useful in a system? So if we want to do something like number of distinct users in the next 60 seconds, you can either wait 60 seconds, or you can give incremental updates to the user, give some sort of feedback. So instead you could say give something every 5 seconds, showing them as the number of distinct users grows. And this gives them feedback, but also they might not need to run this query for 60 seconds. They may be able to terminate early or realize this was not the query they meant to be running and iterate on the query. So let's look at what some of these windows look like. So tumbling windows. Let's say 10-second tumbling window, which means every 10 seconds, we're going to return everything we've seen in that 10-second window. And let's do this for a 30-second time window. So we have record 1, 2, 3, 4, 5, and that's the expiration of our window. So that's what we're going to return back to the users. Then the next window starts, 6, 7, then we return 6 and 7. Now we're going to do our last 10-second window, 8, 9, and then we're going to return to the users 8 and 9. The other tumbling window obviously is the record-based one we discussed. So same time period, same records. Record 1, 2, 3, and now we return to the users. Then record 4, 5, 6, now we return to the users. And record 7, 8, 9, and now we return to the user. And we'll do one more, which is sliding window. This is over, we'll do a second window with the 1 record slide. This means we're always going to return to 3 records every time a new record arrives. Or at most 3 records. If we've seen less, it's going to be less. We're going to do this over a 10-second window because there's not enough space to do more. So if you have 1 record, you're going to return that right away. Second record arrives, you're going to return that right away. Third record arrives, you're going to return that right away. Now with the 4th record arrives, you're going to start aging things out of your window because it's now full with records 1, 2, and 3. Record 4 arrives, the window becomes now 2, 3, and 4. Record 5 arrives, and the window is now 3, 4, and 5. Last set of demos for me to show you how some of these aggregations work. So we'll go back here, and I have a couple of distinct user queries that I will show you. So one is a distinct user time series. This is the same data set as before, where it's our kind of data around our apps or web usage. This is mostly internal data, but it has a reason of testing going on. So what we're going to do here is we're going to do count distinct B cookies, that sort of naive problem we discussed, and we're going to show everything in the window. And we're going to run this for 60 seconds. So after 2 seconds, we start seeing, about 5,000 records in every single window. What we can do instead, we can turn this to time series, and now you start seeing this being appended to the bottom here. And to kind of get a feel for how these are changing, we can also just graph this. And then you'll start seeing a data point added as we keep going, and it'll start smoothing out. And you can see at the bottom, it's about 4,500, at the top about 5,000. That's a pretty consistent volume of records flowing through the system. And I'll just terminate this now. Another similar one will be distinct users instead of time series. So the same exact query. The one thing I've changed is instead of everything in a window, I'm doing everything from the start of the query. So now my count distinct here is going to be growing. And if you see what it's doing is it's growing, but it's growing by a smaller chunk with each iteration. That's because, right, every time I get a new set of users in a window, they're probably overlapping with some users from the previous window. And so the delta of new users grows smaller than the previous window. One other thing you may have noticed here is that this was an integer and now it's a float. And obviously, there's no such thing as 0.73 users. But what's actually happened is we went from being able to give you 100% accurate results to the sketch going over its threshold, and now it's doing estimates. So you can see with this, we have some meta information, and you can see that the sketch that we're using was an estimate, and then you can even see standard deviations and what the possible ranges were for that value. And then I can show you if we go back up a few of these windows, maybe back to window 3, you'll see it's now 1253. So we're still within the sketch size of 16,000. But once we, still there. And then the 5th one, now it's estimating. One last thing before I hand it over to Nate is I want to kind of describe what happened underneath the hood when all these queries were happening, right? There was me submitting a query. There was that query hitting our web service. There was that web service annotating the query with an ID and sending it along to the request processor into the Bullet backend system. The request processor then forwards that information along to the data processor responsible for both evaluating the queries and reading the data, and to the combiner, which is responsible for combining all the data from the data processor that matches a given query. Now, these components are running, and nothing is happening until data starts running. Again, you can put whatever data you want into the system, but once it starts flowing in here, it'll be processed by the data processor. If anything matches to the query, it'll be forwarded along to the combiner, and then the combiner will join that information together, combine it, and then send the results to the Bullet web service and right back to me. All right, and now I will hand over to Nate to give you the nitty-gritty.
Hi, so I'm here. I'm going to talk about a little bit about how Bullet works and the overall architecture of Bullet, and then also at the end, I'm hoping to show you a couple of different instances of Bullet. The demos that Michael showed you were both Bullets set up on our internal audience instrumentation data, We've also set up an instance of Bullet on Reddit's comment stream API, so I can show you that when you can do some fun stuff with that. And we also have an instance of Bullet set up on some finance data where you can get an idea of stock price changes and things like that. So there's a couple more queries, or I'm sorry, demos that I can show you at the end about those. But first, the core design principles for Bullet. I think the primary design principle that drives Bullet's high-level architecture is that there's no persistence. Unlike most query systems which aggregate the data somewhere or save it somewhere and then go scan it for each query, Bullet's only scanning the data as it flows through the system. Once it's scanned the data, it just drops it. So there's no persistence. The trade-off there is, Bullet, because of that, is very lightweight. The queries are very fast, and there's very low storage cost. The trade-off, of course, is repeatability. If you run an interesting query and then want to come back 5 minutes later and run the same query, you're going to get different results because it's going to be run on different data. Secondly, we needed Bullet to scale for data and queries. So each query cost is fixed and should be negligible relative to the data ingestion. And we also wanted Bullet to be very pluggable. So we wanted to abstract Bullet in a way where it can run on top of any stream processor. Right now, the backend, which does most of the heavy lifting for Bullet, is written in Spark and Storm. And it should be able to also read from any data source. We have a very simple Bullet record class, which you can just stick your data into, and the Bullet knows how to work with that. So it's very easily to plug into any data source. And you can also choose different implementations for the pub sub, which is the component that's responsible for sending messages from the web service to the backend, et cetera. So everything's pluggable. And we also wanted everything to be tunable. So for example, you can pick your sketch size in order to fix the sketch accuracy. This is a diagram of the overall architecture for Bullet. Here on the left, you can see that our UI layer is written in Ember. The web service layer is written in Spring Boot. It also exposes REST endpoints that you can use to interact with Bullet programmatically. So for example, you could write a Node.js library that could launch queries directly into the web service, and then you could get the results back from your data as a JSON object and do something with it in Node if you wanted to, or anything like that. And then there's the pub sub layer, which is responsible for taking queries from the web service and injecting them into the backend, and also taking results from the backend and giving them to the web service. And the pub sub is abstracted in such a way where you can implement it whatever you want. Right now we have an implementation with Kafka, and we also have an implementation that just uses REST endpoints that you can launch with the web service. And then there's the backend layer, which is primarily made up of 3 different constituents. There's the request processor, which takes the query. It annotates the query with the query ID and does some bookkeeping. It sends the query to the data processor, which is reading and filtering all the data. The data processor will extract all the data that's required to satisfy the queries that are currently in the system. And then the data processor will send all its results to the combiner, which combines them and sends them back to the pub sub and to the web service and to the user. This is a more detailed diagram of the backend architecture in Storm. I don't want to go into a lot of detail here, but it's here if you want to check it out. One thing I will say is that there is a little bit more going on the lower level. There are signals being passed around and things like that. Bullet does some rate limiting, and so there's some additional bookkeeping going on. It's here if you want to look at it, or you can come up later and ask questions. We'll be here. Similarly for Spark, the architecture for Spark is similar, but I don't want to go into too much detail for this. So one of the core design principles of Bullet is that we wanted it to scale very well for queries and data. And so far, all the performance metrics that we have measured for Bullet indicate that it does that very well. This is one example of that. Here on the x-axis, you have the amount of records that Bullet needs to process. On the left, it's 300 megabytes per second, all the way up to 4 gigabytes per second. And in the y-axis, you have the number of CPU, these are virtual cores, that are required to handle that load of data. And as you can see, it scales very nicely. It scales very linearly. So if your data is changing, or if you have high data, it's very easy to scale Bullet horizontally to handle whatever kind of data you have. Similarly with queries, here on the x-axis, we have the number of CPU cores being used to run Bullet. And on the y-axis, we have the maximum number of concurrent queries that Bullet can handle. And you can see that it also scales nicely, very linearly for queries. I'm going to show you now a couple of demos. Here's one. This is an instance of Bullet that we have set up on Reddit. Reddit exposes some APIs from which you can stream all their comments. So this is an instance of Bullet that's set up reading all the comments that are being made on Reddit in real time. For those of you who don't know, Reddit is a website where you can go and have all these different interests. There are things called subreddits. So like if you're interested in sports, you can go to the sports subreddit and there are articles and videos or whatever. You can go to the movies subreddit or whatever. So this is an instance of Bullet set up on that. In this example query, we are going to be doing a top K on the subreddit field. So we're going to be getting the top 10 subreddits like right now. So it's going to be like for the records that are flowing through the system while this query is running, the subreddits that are found most often are what we're going to be pulled out for this example query. For the windowing, we're going to be doing time-based windowing. So we're going to be sending back results every 2 seconds, and we will run the query for 20 seconds. So as you can see, as the results come back here, the count is being updated here in real time on the left, and this is a really great way to kind of get an idea of what the most active subreddits are right now as the data is flowing through the system. So it looks like the top one is Ask Reddit. Ask Reddit had 28 comments during the lifetime of this query. And second was Politics, which had 24 comments during the lifetime of this query. The Donald, which is a subreddit, I presume, about Donald Trump, had 13 comments during the lifetime of this query. And then there's Anime in Quebec, which I'm not quite sure what that is. And then Rocket League, NBA, Ask Ouija or something, and CFB, which all had 4 comments posted during the lifetime of this query. So that's the idea. Once you have Bullet set up on whatever your data is, it's very easy to run quick ad hoc queries to get an idea of what the data is flowing through the system and whatnot. Here's another example of an instance of Bullet that is set up on finance data. So this data, every time a stock is bought or sold, we get a record telling us the ID of that stock. So maybe it was Apple stock that was bought, and it gives you the price of that stock and the change percent and things like that. And so for this example query, we're going to be doing a distribution on the change percent field. So the change percent tells you every time a stock is bought or sold, it'll tell you the ID and it tells you the change percent, which is the percentage change in value of that stock for this day. So this will tell you in general, and there's no filters on this query, so we're going to be looking at all the data flowing through the system during the lifetime of the query. And we're going to look at the frequencies over evenly spaced points. And again, we will do time-based windowing. So we'll send results every 2 seconds, and we'll look at all the data from the very beginning of the query. As you can see, if we graph this, this will give you a good idea of kind of the overall look of the data. So for example, this data point here says that there were 664 events that flowed through the system, for which the change percent was somewhere between 5.7 and 15%. So these are all stocks that went up, or events representing stocks that went up. Here there were 25,000 events flowed through the system that were somewhere between 3.5 and 5.7. So you can see the buckets we're creating here are somewhat random because I told the query to split up the data evenly with 11 evenly spaced points, so it's kind of random. So I think maybe to see it easier, we can tell it to specifically split up the points the way I want, and we'll just look at change percentages between -12 and -9, -6 and -3, -3 and 0, and so on. We'll break it up perhaps in a more easily viewable way. And if we look at this, this should give us a good idea of kind of what's going on in the stock market in general. All these events that are flowing through the system are being aggregated in real time by Bullet. I can stop auto update here so we can inspect the data. And we can see here that there were 3,700 events that flowed through the system with a change percent from 0 to 3. So these are stocks that went up a little bit. And there were far more events, 23,000 events that went down a little bit from -3 to 0% change percent, and even more, 29,000 events that were from -6 to -3, and so on. So again, it's a real easy way. Once you have it set up on your data, you can run these kind of things and get an overall idea. This generally tells you that it looks like the stock market is kind of on average going down rather rapidly, which is in fact the case. Oh yeah, so that was the demo. Briefly in summary, Bullet is a lightweight and cheap stream query engine. It offers raw records and OLAP style queries. It leverages the power of data sketches. You only need enough hardware to read the data, and queries are basically free. It's an abstraction layer that can sit on any stream framework. It's pluggable and allows for consumption from any data source, and it's fully open sourced. Future work, we're working on something called BQL, which is a SQL-like interface where you can write SQL queries and launch them into Bullet. That's actually already supported in the web service. It'll be in the UI soon. We're doing more stream processors in the future. We're going to finish all the windows and do more aggregations and more. Here are our links. It is all on GitHub. This github-db.github.io is our main documentation where you can learn all about it. It also has a quick start if you want to set one up. It's very easy to set up, and those has instructions for how to plug it into your data and stuff like that. I also encourage you, if you guys want to learn more about it, if you want to try it out, please contact us at bullet-dev@googlegroups.com or bullet-users, I guess it might be better, at googlegroups.com. If you want to check it out, we're happy to help, and we'd also love any feedback if there's features you guys might be interested in, or if it's working great for you guys, please reach out to us.